Welcome to this lesson on transformers and voltage conversion. Transformers are fascinating devices that play a crucial role in our electrical power systems. They allow us to change alternating current voltage levels efficiently using the principles of electromagnetic induction. In this video, we'll explore how transformers work, the mathematics behind them, and their real-world applications. A transformer is an electrical device that changes alternating current voltage levels using electromagnetic induction. The basic structure consists of two coils of wire wrapped around an iron core. What makes transformers unique is that there is no direct electrical connection between the two coils. Instead, energy transfers from one coil to the other through magnetic fields. This magnetic coupling is the key to how transformers operate. Let's understand the working principle step by step. The primary coil receives alternating current, which creates a changing magnetic field in the iron core. The iron core is essential because it concentrates and guides this magnetic field between the two coils. The changing magnetic field then passes through the secondary coil, where it induces a voltage through electromagnetic induction. During this process, electrical energy converts to magnetic energy in the core, and then back to electrical energy in the secondary coil. The turns ratio is fundamental to understanding transformers. It is defined as the ratio of the number of wire turns in the primary coil to the number of turns in the secondary coil. We express this mathematically as NP divided by NS, where NP represents the primary turns and NS represents the secondary turns. This ratio is crucial because it directly controls how voltage changes between the two coils. The relationship between voltage and turns in a transformer is beautifully simple. The voltage ratio equals the turns ratio. Mathematically, Vs divided by Vp equals Ns divided by Np here. Vp is the primary voltage, Vs is the secondary voltage, Np is the number of primary turns, and Ns is the number of secondary turns. This fundamental equation allows us to predict exactly how voltage will transform based on the coil design. Step-up transformers increase voltage from the primary to the secondary coil. This happens when the secondary coil has more turns than the primary coil, meaning Ns is greater than Np when voltage increases. Current decreases proportionally to conserve energy. Step-up transformers are extensively used in power transmission lines, where high voltages reduce energy loss over long distances. Step-down transformers do the opposite by decreasing voltage from primary to secondary. In this case, the secondary coil has fewer turns than the primary coil, so Ns is less than Np as voltage decreases. Current increases proportionally. Step-down transformers are common in everyday devices like phone chargers and power adapters, which convert high wall voltages to safe levels for our electronics. In an ideal transformer, power is conserved between the primary and secondary sides. This means that the power input equals the power output, expressed as Vp times Ip equals Vs times Is. This equation reveals that voltage and current are inversely proportional in transformers. When voltage increases, current must decrease by the same factor, and vice versa. This inverse relationship is crucial for understanding transformer behavior and efficiency. Transformers are everywhere in our electrical infrastructure. In power transmission, step-up transformers increase voltage to hundreds of thousands of volts, significantly reducing energy loss over long distances. For home distribution, step-down transformers bring these high voltages back to safe household levels. Phone chargers use step-down transformers to convert wall voltage to device-safe levels. Industrial equipment relies on both types of transformers to provide specific voltages required by different machinery. Let's recap the essential concepts. Transformers use electromagnetic induction to change alternating current voltage levels without any direct electrical connection. The turns ratio between the primary and secondary coils determines how much the voltage will change. Step-up transformers increase voltage while step-down transformers decrease it. Remember that voltage and current are inversely proportional maintaining power conservation. Transformers are essential for efficient power transmission and distribution, making modern electrical systems possible. Understanding these principles gives you insight into one of the most important applications of electromagnetic induction.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.